Hello, everyone. Welcome to another interesting and exciting tutorial section. Today, we will be solving another question relating to phase equation of soil, phase relationship of soil. But in this question, the phase equation is going to be related to other geotechnical engineering concepts. So here we'll be relating phase equation with compaction. We all know that compaction is the removal of air from the voids of soil. So today we'll be relating phase equation with compaction. So one thing we have to know is we have to write out the parameters given, and as we can see, the weight of a soil sample retrieved by a field technician is 411 pounds. So parameter we have weight, that is the weight of soil. So this is actually a feed density test. So let me briefly explain what they do whenever they conduct a feed density test. So the essence of conducting a feed density test, just like the name implies, feed density, is to obtain the density of a compacted area or a side or a surface. So the essence is just to know the dry density on site. Then after getting the dry density, you now relate it to its maximum dry density that was obtained in the lab. So with that, we'll be able to know the how much have we compact the soil. So we'll be able to get the degree of compaction, just like what they are asking in the question. So let's just briefly explain what happens in a feed density test. So this is your soil surface, just like subgrade, pavement subgrade. Let's say this is this is the plan view. As a plan view, they make a hole. Then let's draw our cross section. So they make a hole. So it can be a little bit deep. So this is section A prime. So this is a section A prime. So they usually make this O. So they make this O, and they bring out the soil material. They bring them out. So that is the weight they give to us. Total weight 4.11 pounds. Then they determine the water content. So let's say this is a jar. So they put all the soil that was taken from the O into this jar, sample jar. So after that, you now determine the water content. So they gave us the water content also. Water content is 19.2%. So that's water content. So now we are left for us to know the dry density on site. We need the total density force, which is the total weight of total volume. So how do we now know the volume? How do we want to know the volume? How can we obtain the volume of this shape? So that is where the concept of sound replacement method comes in. So with that, they use a soil with known density to obtain the volume of this shape. So that is why they gave us the volume using the unit weight of a known material. So I don't want to go in details regarding feed density. So you obtain your dry density. So let's just proceed with our question. So we know this total weight of the soil. Okay, and for we to know the total volume, we have to use a material with known density. So total unit equals to weight, total unit over volume. Volume equals to what? Total weight over total unit weight. So we would it's like it's a sound replacement. It has a funnel like shape. So it's like that. So you know the weight initially, then you take this funnel to this hole, you place it on the hole, then you release the soil into the hole, then you know the weight final. So the difference between the initial weight of material in this initial weight of soil in this funnel and the final weight of soil in the funnel after releasing into the hole will give us the weight of soil in the hole. So we know the weight of soil in the hole. Since we know the weight of soil in the hole and we know the unit weight of the material, then we will know the volume of the hole. That is how they obtain this volume of hole. So that is how feed density is being carried out using the sound replacement method. So let's proceed with our question. So first thing we have to do is to obtain the total density. We know that our volume is 0.03 feet cube. So total is going to be 1.1 total weight over total volume. That is total weight over total volume. It will be equals to 4.11. 4.11 divided by 0.03. So we have in 137 pounds per feet cube. So that is our total unit weight. And we know the relation between dry unit weight and total unit weight is this. So we can obtain over 1 plus water content we have that we've been given 0.192, which is equals to divided by 1.192. So 114.9 pounds per feet cube. So this is the dry unit weight in the feed. So for we to know the degree of compaction, we have to relate it with the maximum density. So in the lab, they usually conduct a test called the compaction test. We have different types. We have proto, we have modified H2, and many more. So they varies based on depending on they are all compaction tests, but the major differences are just the weight of Rama. They all have different weight of Rama. The weight of Rama, the size of the mold, and the layer at which you fill the soil sample in the mold. Some are 3 layers, some are 5 layers. So they vary significantly. So depending on the method you want to use, so you obtain, they all give you same, they don't give the same property. I mean, they give they help us obtain same property, which is called the maximum density and the optimum moisture content. So this result will vary depending on the comparative effort you use. So the maximum density you obtain in a proto test will be different from that of the modified H2 because of the difference in the size of mold and the weight of Rama. So but in general, we obtain two major parameters. So we have on the x-axis we have water content. So when you start compacting, the dry density will be increasing. Then later on it reduces. So we show you have a cup like this. So we show this is 0 air void. This is at S equals to 1 at full saturation. So now they've already given us the maximum density, that is 132.3 pounds per cubic feet. They already gave us that. So we can now easily find the degree of compaction. So degree of compaction is the dry density, dry unit weight in the feed over the maximum dry density, dry unit weight in the lab. It's close to 137 over. It's close to 114.9 over 132.3, which is close to 86.9. 8%, which is approximately 87%. So most of the time, if you check most of the code, this seems very low. Most of the time, it's depending on the structure, it ranges between 92 to 100% degree of compaction. So when you do that on the feed, you relate that with the maximum dry density. That is the maximum dry density it can obtain, that can be obtained based on a certain compactive effort. So we already obtained that. Then we use that to control our compaction in the feed. For example, now we see that in the our degree of compaction is 87%, and let's say the target percentage is 95%. Let's say we're targeting the degree of compaction to be 95%. So we have to continue our compaction until we obtain. For example, let's say the target degree of compaction is 95%. So we have to keep on compacting so that when we relate our feed density with our maximum dry density, it will give us 95%. So that's how it's being done. It helps us to control our compaction on site. Please, if you have any question regarding this problem we just solved, please drop them in the comment section, and please like, share, and subscribe to the channel. Keep on anticipating for more videos, and thank you.